No, bro. That photo does not look good. Okay. Okay. This is being recorded. Could someone go? Could you check the HCAN teams again? Thank you. Thank you very much. Can you see my screen on the HCAN teams at all? Wow, you could hear it. That's crazy. So my screen is not there? Okay, cool. As you can see, I am a master at this. Share video? Share screen. Never mind. With audio. Is it on there now? Yeah, that's on here. Sweet. Okay, cool. So, yeah, like I said, 5 questions. If anybody wants to take a photo of this, please do. I'm going to read it out here just a sec. Okay. So the current-driven network shown in Figure 1 is operating in the zero state condition. That is, the inductor and capacitor have zero initial conditions. Using the components shown in the schematic, you are asked to do the following. Derive the ODE based on that. Express the ODE in the usual time domain form of that. Also, calculate the values for the undamped natural frequency and the dampening ratio zeta. Describe the nature of the response, i.e. overdamped, critically damped, underdamped, undamped, and oscillatory. Show all your work and explain your assumptions made. So, all right. How should we start this? Anybody have any ideas? It is also behind y'all if you, or on the left if you don't need. I guess that's the right for y'all. You could do that. We could do that. You eventually, yes. How would y'all? What are some main methods of solving circuits 2 problems? Like MAME. Yep. Yes. Those are different things. I would say the Thevenin's and Norton's no, because we use MAME and name usually to find that. What's up? We can convert, like, and kind of combine the middle ones, right? You saying something about here? Yeah. I will get. Yeah. Yes. You could. You could. I see where you're. I didn't do that, but you could do that. You could just do MAME and name or MAME. What's up? No, because I did KCL and KVL, and in my mind that actually made more sense because I just didn't want to deal with anything. So we're gonna stretch KVL, KCL muscles. So if y'all don't have those much, I understand because I didn't really when I did this problem. It took me a second. So one thing, if you look at this, you can kind of look at this in a name scenario. If you see here, we got the VN term here, okay? So that means we just kind of finding the nodal voltage. Well, nodal voltage, you assume name. But name doesn't really make sense to do here because it's just all one node. There's nothing up top breaking it up. Do y'all know what would like make things 2 different nodes? Like, how am I saying that this is just one node? Exactly. Okay, so like I said, nodal voltages, whatever. So you can kind of go based on name. And when I think of that, I think I need everything in current sources. I want to know how current is flowing everywhere. Okay. So I say that, but I'm also about to use resistances. So I guess maybe not. But I want to know how current is flowing everywhere because I have a current source going that way, which is also coming in that way, which is going that way, that way, that way, that way. Do y'all agree? Okay. So we're just going to add everything up. I'll start. Does anybody see any issues with what I have? Not the arrows, the actual circuit itself. I was kind of talking about name and how there's sources and stuff like that. I have a voltage source. Now you could technically leave it there if you really wanted to, because we only want to know what the direction of current is flowing. But if that's a source, even if this is a voltage source, how is current going to be flow? What direction is current going to be flowing based on the polarity of this voltage source? Okay, positive. But what do you mean by that? Straight up. I agree there. So I'm going to use these arrows and add everything up. Okay. So I'm literally just going to use V equals IR, KVL, KCL, well, KCL at this point. Okay. So also my handwriting sucks. If y'all have any questions, literally just ask. So, yeah. Okay. So from the left, I have JG of S kind of feeding everything. Okay. So I have that nodal voltage, right? So the VN, I'm just going to make everything of S, divided by R1 gives me the current in that branch. Y'all agree? Okay. Now we're going to the next branch. Okay. What is the resistance, impedance of that capacitor? Is it SC2 for the impedance? 1 over SC2. So 1 over SC2. Okay. So in that branch we have that, but we also have that current source. Oh, well, it's not a current source. It's a voltage source. But I'm just going to look at it as in the direction in which the current would flow. Okay. Would you say it adds or subtracts to the current in that branch? Subtracts. Okay. What would you say the value of the current is on that source? So, what's up?
There's those two elements that make up that current in that branch.
Correct.
The source and the capacitor.
Correct.
To use the impedance of the capacitor.
To do what?
Multiply it, or V over R equals current.
Correct.
So voltage over the current.
Correct. So what I would do here, like we said, since it is opposing. I just turned it off. I'm sorry. I don't even know how I did that. Okay. Sorry. Since the current direction is opposing that branch, we've already said that it is subtracting. But like we said, the voltage of that voltage source is Rm I3 of S. And like you said, we need to divide it by the impedance of that other element, which is the capacitor, 1 over SC2. We're done with that branch. We just take the impedance of it because every element has impedance. And just in this case, you know, it's in the S domain. We're changing everything to the S domain to make it easy. I'm not doing a freaking differential equation until the end. Okay, so we got, what's up? Okay, we got one more thing to go. What's the current in that last branch? This one here. Any guesses? We're still using that nodal voltage, right? We have to, you know, voltage divided by impedance, sorry, gives us current. I agree. What is the impedance of that inductor? Yep, that's L4. That's fine. Okay, so we have what do you call it? We have we have 4 terms here. 3 of them have V in it. One of them has I3. What is I3? We want it in terms of the nodal voltage. So we want to find current over through V equals IR. So V over R. Yeah, so just this. All right. I3 of S equals Vn of S over R3 plus SL4. Okay. So I don't like these like this. I really don't like it. It's a fraction. Fractions just are annoying. What is 1 over 1 over SC2? What would that be? Exactly. So literally we can just make this. I'm going to rewrite this. Vn of S over R1 plus. I'm also going to factor out like terms and just multiply everything together. Vn of S. I'm just going to keep this right here and we'll change it here in a sec. Times SC2 plus Vn of S over R3 plus SL4. Does everybody agree with that? Let me make this C actually look right. Does everybody agree with that? With what I did? Does everybody understand how I got from here to here? Yeah? Cool. Cool. All right. So, like I said earlier, this is equal to I3 of S. So I'm just going to put it in. JG of S equals Vn of S over R1 plus Vn of S minus Rm times, I'm going to make it like that. We're just going to do this. Rm Vn of S over R3 plus SL4 SC2 plus Vn of S R3 SL4. All right. Is there something alike in every single term? Does every single term on the right have something in common? Yeah, I'm going to take that out. I'm also going to divide it over, just to make it easy for me on the left side. By the way, I do primarily things in algebraic form. You got to, I didn't charge that calculator. You got a fancy calculator, use it if you need it. There's in later questions, I did use it very heavily because I was not about to do that freaking algebra. It's annoying. I did do it when I was in circuits 2. I was better at it back then. It's been a few semesters, but yeah, I would definitely say use that calculator. If you have any questions on how I do stuff later with my calculator, let me know, and I will try to do my best to talk about it. So, okay, I'll keep going. All right, so like I said, I'm just going to divide out the Vn of S. So it becomes Jg of S over Vn of S equals 1 over R1 plus 1 minus Rm over R3 plus SL4 SC2 plus 1 over R3 plus SL4, right? I'm going to go ahead and multiply that SC2 in, just so it's a little easier for my brain. I kind of took it out, put it back in, whatever. So that would then be SC2 minus RM SC2 over R3 plus SL4. There we go. That makes more sense to my brain. Okay, so now I'm going to kind of try to make it where they all, I'm going to try to get rid of the fractions. So I can then, I'm going to write this over here. These all have the R3 plus SL4. I'm going to make it like a common denominator. That's basically what I'm going to do. All right, so I need to multiply this term here by these terms to get that common denominator. Does everybody kind of see where I'm going with that? Yes? No? Any questions? Okay. All right, so then I'll have the R3 plus SL4 times the 1 over R1 plus SC2 minus RM SC2 plus 1. And that's all going to be over R3 plus SL4. Okay. So I'm just going to rework some things. I kind of do things a little out of order. So if it doesn't make sense in your head, you are more than welcome to try it, your method, and just make sure y'all get the same thing, because I've double-checked my answers from Russell's, and it's the same. So I'm then going to multiply over the R3 plus SL4 to the other side. And eventually we want to get current on one side, voltage on one side, so then I'm going to multiply over the Vn of S. Vn of S times R3 plus SL4. I'm going to make that better. R3 plus SL4, 1 over R1 plus SC2, minus RM SC2, that's a 2, plus 1. Yay, nay, makes sense? Cool. I'm going to do this a little bit better. Okay, now I need to multiply out this thing. I don't want this thing staying here. So I'm going to multiply that in. All right. Is everything making sense so far? Anybody got any questions? No? All right, cool. Does anybody want to take a photo of the question? No? I'll give it just a sec if you want to take a photo. If anybody wants to take it. This is the problem I'm working on. This is just number 1. I got 4 more after this. So, yeah. Cool. All right. So, like I said, I'm going to multiply out this so it just is better. R3 SO4 on the left, Vn of S. That gets me R3 over R1 plus SC2 R3 SO4 1 plus S squared C2 L4 minus RM SC2 plus 1. Okay. That is all of that. So, does anybody have an idea of what I should do next? Oh, shoot. That's fun. Okay. Am I still? Nope, not there. Nice. Oh, shoot. That's going to be fun. Okay. Is it? Wait, no. I want to start broadcast. I'm sorry. Okay, there we go. I don't do this often. If you can tell. All right. All right. So, should I explain what I've done or just keep going? All right, let me. Would you like me to go over that again, or what is his name? Jose. Would you want me to go over that again, or no? Or Juan? I'm sorry.
We're good.
Okay, cool. Just double checking. All right, cool. Well, then I'll keep going. Does anybody have any idea of what I should do next? Thank you for that. What do you mean by standard form normalizer? I like where you're going, but what do you mean?
Order it from the highest power to the lowest power.
I like that. That's exactly what I'm going to do. JG of S, R3 plus SL4 equals Vn of S. So what's first? Tell me what's first. Yep. S squared C2L4 S. I'm going to group everything in the S's and just make one big term. So I have this term has an S, that term has an S, that term has an S. So I'm going to group it all together. Yep. L4 over R1 plus C2 R3 minus C2 RM. And then we have two terms without any S's. So then that'll go there. R3 over R1, that's a plus, and that's a plus 1. All right, what was the second part of what you said? All right, cool. How do we normalize it? So this, in this case, what would that be? Divide what? Well, correct. What's connected to that? Yeah. So literally just divide the entire problem by C2 L4. So then I have a JG of S. Let me do this. JG of S times R3 plus SL4 over C2L4 equals Vn of S times S squared plus, this thing gets kind of nasty, but whatever. Let's see how I want to do this. That L4 over R1 plus C2 R3, yep, minus C2 R1. That's RM, I'm sorry. That is RM. Yep. All right. All divided by that C2 L4. And then I take the term with no S's. And then I divide all that by just C2 L4. R3 over R1 plus 1 over C2 L4. All right. Does it make sense so far what I have done? Any questions? No? We good? All right, cool. So at this point, I said, screw it. I'm not doing anything in terms of putting in actual numbers here. What I did was I put it in a calculator, because what I did was I set all these terms here, like the L4 and all that, to their numerical values in my calculator. Does everyone know how to do that, to store variables in a calculator? Anybody know? Okay, cool. We're all good? So that's what I did. And after I got that, it was a lot simpler. I also just factored in, the Vn of S and JG of S. So what I did, I'm going to have voltage on my left, current on my right, just so it kind of has the better form of this, right? I'm kind of just moving stuff around. Like I said, it's a little mixed match, but yeah. So what I did on the left, like I said, I had the nodal voltages and I multiplied everything in. So I had the V in of S times that S squared. Okay, I'm still in the S domain. We're not to the ODE yet. Okay. When I put this in my calculator, this whole term, this is what I got. Well, I'll do the V in of S times S, and that value, this value here, when put in the calculator with all the numerical values, becomes 2.5 times 10 to the 6th. That's it. Plus V in of S is the next term. Then I put all the numerical values in my calculator of this term, and I got 25 times 10 to the 12th. Okay, cool. All right, now this term here, same thing. I put it in my calculator, and I multiplied in the JG of S. So what I got was JG of S times S times 10 to the 9th. Okay? Which one? It's 25. So I got JG of S times 10 to the 9th. That's what I got. Then it also had a next term, JG of S times 18 point, I'm going to go in a little bit, sorry. 18.75 times 10 to the 15th. Okay. That is what I did when I just put everything in my calculator, made it easy on myself. That's what I got. So can anybody tell me what we do next? This is kind of like the easiest step in my opinion. Sweet. So I'm going to turn everything into the time domain. V n of t, what does the S squared become in the time domain? I agree. Okay. V n of t times, what does S become? What does just S become in the time domain? Just t? Well, d over dt. D over dt times 2.5 times 10 to the 6th plus V n of t times 25 times 10 to the 12th. JG of S becomes JG of t times d dt times 10 to the 9th. Yep. Plus JG of t times 18.75 times 10 to the 15th. I'm going to write that a little bit better. Okay. So that is 20% of the test. Congratulations. You got a 20. What do we do next? What do we do next? We got this part done. Now we need to do that part. Not specifically. Not for this question. Like, well, it's saying calculate the values for the undamped natural frequency and the dampening ratio zeta. So there's like a couple. I wouldn't call it the holes or the poles. I wouldn't call it that. I would say we use these equations, the ODE, and we use terms from that equation to find the natural frequency and the undamped natural frequency and dampening ratio. Does anybody remember what those things are? So I'll start here. Undamped natural frequency is omega n. Does anybody remember what omega n equals? From this is so this here. What's up? No. So this whole term here is simply, I'm just going to go back to algebra where we just have x's. X squared plus a2x plus a1. Okay? Like that is the form this is in. This polynomial equation, this is the form it is in. So we have, like we have here, x2 is just the second differential. A2x is the d over dt 2.5 times 10 to the 6th. A1, 25 times 10 to the 12th. Does that make sense? Does that make sense? Okay. So does anybody remember the equation for the undamped natural frequency with that in mind? No? It's the square root of A1. Just A1. So this is important to remember. Omega n, square root of A1. And from what I just wrote down, probably shouldn't have erased that, but whatever. Let's see. From what I just wrote down, can anybody tell me what A1 is? Yep. Omega N. What is omega N in units? As in, what is our undamped natural frequency? What's its units? Does anybody have an idea? I agree. Now, the numerical value is just 5, and this is going to be mega radians per second. What is mega? I agree. Okay. We're halfway done. Boom. Okay, cool. We're halfway done. What is the dampening ratio? Does anybody remember the equation for that? No? Yay? No? Maybe? No? Okay. It's a little bit more complicated. So zeta, by the way, this is all in his materials, or you can just refer to this, whatever you want to do, is A2 over 2 times the square root of A1. It's that easy. What is this term, though? Square root of A1. As in, what is the variable we found with that? Bingo. So this is literally just A2 over 2 times omega n. And so that just becomes 2.5 times 10 to the 6th over 2 times 5 times 10 to the 6th. Put that in, you get 0.25. Now, can anybody tell me, there was one other caveat with this question. I'm going to scroll up. Can I scroll up? Has everybody got the answer on that? Okay. Describe the nature of this response. Overdamped, critically damped, underdamped. I'm sorry. There's an over. Yeah. Overdamped, critically damped, undamped, or underdamped, sorry, or undamped or oscillatory. These are technically the same thing. Don't be fooled. Those are technically the same thing. Technically the same thing. Can anybody tell me if this zeta equals 0.25 is underdamped, undamped, underdamped, critically damped, or overdamped? I agree. Why do you say it's underdamped? Exactly. So I'm going to write that down for everybody who didn't hear that. If zeta equals 0, that is undamped or oscillatory. Let's see if I can spell that word. Okay, that's the first time. If zeta is between 0 and 1, it is underdamped. As in what our equation or our problem becomes. Okay. When zeta equals 1, as he just said, critically damped. And if zeta is greater than 1, overdamped. So that is very important to know. I'm going to be honest, I'm not too sure.
Isn't that going back to the exponentials? Like when you write e to the, if it's greater than 1, it's going to be.
It's just going to keep going.
Keep going. The envelope is going to keep rising.
Yeah, that makes sense. So basically, if it's undamped, that thing's going forever. It's just going to get larger and larger and larger and larger. Yeah, kind of. It's just gonna keep going. It's gonna keep going.
Yeah.
So like,
the envelope is what it keeps it like as to what it is.
it's like the bounds, and then that'd be like undamped, basically. As a very, very rough sketch. So yeah. Any questions about this problem? Any questions? So I've been doing this is my 3rd semester doing this, and this is the most annoying problem I've had to do because the other 2 problems that I've done I've been name. So this is the most annoying. Yeah, if you want to see any other 2, either a name or name for this, I have 2 reviews up on I think like the HCAN YouTube channel, and they're also pretty helpful, I'd say. So yeah, cool. On to the next question. And by the way, this has been on the test for the last 3 semesters. So I should say this type of question where you're going to find the ODE, where you're going to find natural frequencies and you're going to find the dampening ratio. That's been on the test for the last 3 semesters. If he does not put that on the test, I will be extremely shocked. Okay, so moving on. Actually, any other questions though? We good? Yay, nay? Cool. All right, so next question. Let me read it out. The linear RLC network shown in figure 38 contains a pair of dependent sources. This network is a zero-state network where all initial conditions are zero. With the component values shown in the schematics, you are asked to do the following. Write out fully the S-domain mesh analysis matrix equations, or MAME, in the usual form of that, where the vector IM contains mesh currents as unknowns, express the matrix, blah, 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 numerical form. Do MAME. Then use Cramer's rule to find what is that called again? What is Y of T of, or YT of S? What does that stand for again? Transits. There we go. Yes, transits, yes. Defined as that function there. Express Y of T as a rational function of S with the coefficients N of S and D of S and normalized in the highest power blah, blah, of S. Basically, K N of S, or K N over D. That's it. All right. So, does anybody have an idea of how we should start this? MAME? I agree with you there. How do you want your arrows? I hope you say one way because I only did one way. Yeah, cool. Boom. Boom. Does anybody do their arrows the other way? Just generally curious. No?
Wouldn't your answer be negative because they're all designed to be?
Yeah, it works. It still works. You just have to keep your polarity different. So you could do it the other way, but I'm curious if anybody does. Does anybody? No? All right, cool. I mean, there's people who write left-handed, so I don't know. They could do that. All right, so what is with MAME? What do we use? Like, what are the components in MAME? Okay, I agree. Cool. So, what is the impedance in this first mesh? Yeah. Well, I'm gonna do it in what do you call it? Variables, not.
Okay.
Okay, cool. Yep. 1 over SC3. I agree. Why would it not be that? No. So whenever it's in the mesh, period, you can put it in both. It is connected. Like if you look in the loop, it is in mesh 1 and it is in mesh 2. So you would put it in both, but you'd also put it in the shared ones. Does that make sense? Sweet. Okay, well you said shared. So what goes on to the right? I agree. What goes here? Okay. So now what is in my bottom right? I guess my 2-2 element. Yep. 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 All right. Cool. Yep. In terms of how you start, no. But after you manipulate your dependent sources, it will be. So, but in terms of starting, no. Okay, so then IM1, IM2 equals. All right, what do we got? Okay. And? Do we have anything else in that mesh? What do we have? Okay, is it positive or negative? Bingo. Does everybody understand why? Why it's negative? Why is it a negative EG of S? Does everybody understand that? Yeah. Okay. Okay, what's in mesh 2? In terms of the sources. Is it positive for, what are they positive or negative? Both. Boom, I agree. EG of S plus RM I5 of S. Okay, so we have terms here that are not sources or mesh currents. What do we do?
You have to find out what they are and then separate them out into different mesh and subtract them.
Yep. Okay, so what is V of we're gonna wait on that one. What is I5? I5 is going down in what direction is it? What is I5 in terms of mesh currents? Let me just ask that. IM2, is it positive or is it negative? I agree. If we were to switch the polarities like we were talking about earlier in terms of counterclockwise, what would it be? It would have been negative, yes. But it's IM2 in this case. Okay, so VA. This one, it doesn't suck. It's just annoying. So what is VA? Anybody have a idea? So it is the current on this branch, okay? It's the current on that branch. I agree in terms of current, but we can't just get voltage from current. What do we have to do to it? Technically impedance, yes, but what is the impedance we multiply it by? What? I disagree. Almost. I like your first term. I don't like the EG of S thing. You could technically do it that way, but I just wanted mesh currents. We don't have to do.
Would you have a positive SE3 and a negative SE3?
Technically. So someone said IM1 minus IM2, right? We agree with that. But like I said, we can't just get voltage from current. So we have to multiply by an impedance. What is the impedance in that branch? To then get us that 1 over SE3. So to get voltage, we do the, oh, I'm in laser form. We multiply the impedance times the current, which we agreed was IM1 minus IM2. Does everybody see how I did that? Everybody agree so far? Makes sense? No. Because if you notice, we're taking this in terms of passive elements. So this is not technically an active source, right? IM1, is going into the positive end of VA, and IM2 is going into the negative. You see that? Okay, cool. That makes sense? Everybody else got that? Sweet. Cool. All right, so let's just apply that to what we have. I'm going to separate it out. No, I'm not. I'm going to put everything into a thing and then separate it out. All right, so we then have to substitute. So mu times VA. Found out VA is S1 over SE3 times IM1 minus IM2. And then EG of S. That's pretty easy. EG of S. And then plus RM IM2. So now I'm going to separate it in terms of dependent and independent. So then here we have a negative EG of S. Am I going too fast or are we good?
What is that on your second row? Something S plus RM IM2.
Something S plus IM2. Oh, this is EG of S. You talking about this? Yeah. Okay, sorry. Let me write that better. EG of S. So then, moving on. Oh yeah, am I going too fast or we good? Cool. EG of S. EG of S. I'm separating into dependent and independent. Plus, okay. So then we'll have, never mind. Give me 1 sec. Technically, we will get there, but my bad. I'm just going to multiply everything out a little bit more just to make it easy. Wait, hold on a sec. Did I miss something? I missed something. My bad. So, technically, this is almost correct because it's the voltage on this node here, but we have to take into account that. As in we have to take account the voltage on that, of the voltage of that source. Yeah. My bad. What's up? Okay, cool. That is my bad. So that would then be plus EG of S. So I'm going to write that better. Does everybody understand where I got that? Yeah? Okay, cool. All right, now I'm going to multiply everything out because stuff can cancel. Okay. So I then have a mu 1 over SC3 IM1 minus mu, I'm going to write that better, mu 1 over SC3 IM2 plus mu EG of S minus EG of S. And this just becomes EG of S plus RM IM2. Okay, so this looks kind of screwy. It's kind of sucky. There's a mu there, kind of screwing everything up. I'm gonna take a second, let y'all write that down, and then I will explain where I'm going. But do y'all agree that mu's kind of sucky? Well, we're about to make your life a lot easier. Can I scroll up? Okay. Mu. What's mu? It's 1. So we just have essentially EG of S minus EG of S. They cancel each other out. I'm going to keep the mu's there for the other places. Why do I say this? No, I'm not. Never mind. I'm going to move on to then canceling those out. These cancel out. And then these go here. So mu is just 1. Never mind. I'm just going to say mu is 1. Mu is 1. Now I'm going to move it into dependent and independent sources. So in this top part, we now have zero independent sources. So we have 0 there. And this one, we just have EG of S. Okay. So then for IM1, we just have SC3, S over SC3, 1 over SC3, I'm sorry. For this one, we then have negative 1 over SC3. We then have 0, RM. That looks like a little RM. This is all multiplied by IM1, IM2. Can everybody see how I did that? Yes, no? Yeah. Sweet. Cool.
We're still on the right side of the equation, right?
Correct. Yes. Sorry, I didn't preface that, but yes, we're on the right side. Yeah, we're on the right side. So now I'm going to subtract everything over. Okay. So when I do that, I get a left side of R1 plus SL2 plus 1 over SC3 minus 1 over SC3. I get a minus 1 over SC3 plus 1 over SC3 minus 1 over SC3. And then finally 1 over SC3 plus R4 plus SL4 minus RM. Man. Okay. And that becomes IM1, IM2 equals 0, EG of S. Well, I can cancel out 2 terms. Boom, boom, gone. Everybody see that? Make sense? Sweet. I'm going to rewrite the equation. That's 0. That's 1 over SC3 plus R4 plus SL4 minus RM. IM2 EG of S. Cool. We had a good pace. I'm going to speed up, slow down. We good. But does everybody agree with how I did that so far? Okay. Now I'm just going to put in terms or put in numerical values. In this case, R1 is 6 ohms, L2 is 4 henries, C3 is 1 over 3 farads, and R4 is 2 ohms. I didn't scroll up. I can if y'all want, but those are the values. So when I plug those in, I get 6 plus 4S, 0 minus 3 over S, 3 over S plus 5. There we go. Yep. I'm sorry, that's just S. That's that's S. I'm sorry, that's S. What's up? Sweet. 0 EG of S. All right. We have technically finished we have finished part 1. Yay, we got probably half. We've done the main. Okay. Next part, use Kramer's rule. Good old Kramer's rule. To find the transmittance, which in this case is I5 over EG of S. Okay. Can someone tell me what I5 is? Well, I shouldn't say that. We have already found out that I5 equals IM2. Okay. All right. Kramer's, everybody's best friend, right? We love Kramer's. Okay. If we are looking at IM2, okay, we are looking for the current, or the IM2, sorry. Does anybody have any idea how we should go about doing Kramer's? Kind of? Okay. Walk me through it.
If we're looking for IM2,
Mhm.
we're looking in the mesh, or the current in the mesh of IM2 from the perspective of the first mesh,
Why do you say first mesh?
or where the independent voltage is.
Okay. I agree. Where the independent source is. We're looking from the reference point of the independent source. Where is the independent source? Okay. What would you say? Technically, we need to put it in a mesh. It is technically shared, yes, but we need to. You put it in mesh 1. Does anybody have any other ideas of putting it in mesh 1 or mesh 2? No. Does everybody agree that he thinks it's mesh 1? Does everybody agree with him? I'm just a general question. Why do you say mesh 2?
Don't you, like, I remember it being the determinant,
Mhm.
right? It's for Kramer's rule. The triangle with the 2 subscripts.
Yeah.
The first one is where the voltage source is,
Mhm.
and the second one is the mesh of the current, right?
I believe so, yes. Where I agree with your. We look at the reference and we look at the where the current source is. I don't agree with you saying it's in mesh 1, because theoretically we could do this. That doesn't exist anymore. We now have mesh. We just have mesh 2. Like, we can look at mesh, and technically because we have that source in between both, we can take it. I guess we could take it from whatever mesh. It wouldn't really make sense to take it from mesh 1 because it's already in mesh 2. It doesn't really make sense to go farther. You know what I mean? Because if we could technically take out this mesh right here, then we could still find the current through that node. Now, if the current if it was over here, that voltage source, it'd be different. We would put it in mesh 1. But since it's kind of shared between the two,
So why doesn't that dependent voltage source affect the current?
because we're only looking for the independent source. We're looking at it in reference from an independent source, not a dependent source. Dependent sources, we only look at.
That dependent source is affecting I5 in the actual.
I'm not too sure on that one. I'm honestly not too sure on that. If that was an independent source, different story. We'd make that a reference. But because of that, we then have the fun thing of we put the -1 to the ij, or I plus j, which in this case they're both 2, right? Times delta ij, which in this case is just 2 over delta, times eg of s. Okay. Well, what is -1 to the 2 plus 2, which would be -1 to the 4th? What is that? Just 1. So in that case, it's just this. Delta 2 over delta times Eg of S. Does it make sense what I said in the Kramer's? Yes? Yes. Yeah.
For your reference source, right? You say that the reference is EG of S because it's in the matrix or because it's in Kramer's rule? You see what I'm saying?
Say that one more time.
Like, you're saying that the reference source,
Yeah.
right?
Yeah.
Is EG of S.
Yeah.
And you're saying that because EG of S is in the matrix on the right-hand side, or you're saying that because EG of S is the bottom side of the Kramer's rule?
You're saying that EG of S is the
I'm not too mathematically. I am not too sure. I am not too versed in how that all works. It could be because it's in the matrix, the right side of the equation, in terms of how Kramer's rule actually works. I'm not too sure. I think Russell does have materials on that. How I use Kramer's is literally just applying it to the Maimon name. I'm not too sure on how it mathematically works. It would make sense that it would be because of the matrix, because in math, we're not solving for currents or voltages. We're not doing that. So it makes sense that it would be because it's in that.
But like you always treat the reference.
Hold on a sec. You're on to something. Because if you look here, the independent source is in the second mesh.
Yeah.
So I guess that makes sense too. I'm going to say tentatively it's because, or not tentatively, possibly it's because it's in the matrix. It's in the equalized matrix.
Yeah, but how is that like you cross out row 2, column 2, and that's what you choose? How does that work?
Oh, it's because of that delta ij, right? We have the reference and we have the what we're looking for.
Oh, so it eliminates everything that we don't want.
Yeah. Yeah. So, does that make sense in essence of why we did delta 2 over delta?
Yeah. My only other question is, say on the right hand side of the matrix.
Yeah.
EG of S was on the top side.
Yeah.
Would that change how you do it?
I believe so. I think that'd just be 1, 1, 2.
If you were finding IM2 still?
Mm-hmm. Yes, if I was still finding the IM2. Because delta 2, 1. 2, 1. It would be 2, 1 in this case. That is because, as we've kind of figured out, since the EG of S is in the second part of our matrix,
Figure out where EG of S is.
I would say so. I would also say really look into Russell's materials because he has something on Kramer's, and I assume it would answer that question. Yeah, I kind of want to dig deeper in that, so I might have an answer by next week because y'all's test is literally a week from now. Yeah, that's crazy. Keep switching back, but yeah, I'm pretty sure Kyle was onto something in terms of it's because it's in this part of the matrix. It's in that second mesh. So yeah. All right, moving on. Well, that Y of T is just IM2 over EG. So the EG of S is cancel out. It becomes YT of S equals delta 2 over delta times EG of S divided by EG of S. Those cancel out. Y of T of S equals delta 2 over delta. Does that make sense? Yay, nay, maybe? Cool. All right. What's delta 2? Why do you say that? Boom. That's left. Okay. So that means YT of S equals 6 plus 4S times the determinant, which is top left multiplied by bottom right multiplied, or minus, bottom left times top right. Well, what's top right? So that term just is literally 0. So the denominator becomes 6 plus 4S times 3 over S plus S. Okay. So,
Is that an acceptable final answer?
no. We gotta normalize it. So, numerator, still gonna be 6 plus 4S. Okay. Denominator, when you multiply that together, it becomes, I'm gonna put it also into the highest form of S. 4S squared plus 6S plus 12 plus 18 over S. Does anybody see anything wrong with this? Yeah. We have to get rid of the fractioned S. I don't like this S in the denominator. So how do we get rid of that? Say that one more time. I guess you could do that. That is one way to do it. I also just like saying S over S because it's just 1. You could do that to do S over 18 over S over 18, but I'm just going to do this. Makes it easier in my mind. And whatever you do to the denominator, you got to do the numerator. You have to do the denominator, or vice versa. So that becomes 6S squared plus 4. I'm going to put the numerator in the highest terms. This then becomes 4S squared plus 6 over 4S cubed plus 6X. There's supposed to be an S there. 6S squared plus 12S plus 18. Okay. Here, I don't know about y'all, but I do not know how to factor a polynomial to the third. So I put my handy dandy calculator and say, I'm gonna factor out the roots. Let me explain how I do that. Does everybody know how to do that? Kind of find the okay, cool. Well, I'm gonna explain that. Does everybody have their calculator on them? Anybody? Yeah. Okay. Cool. Mine might die, so I might have to use somebody's.
You can go ahead and use mine. Just do it.
I mean, I already have the answer, but I'm just finding this. Is it factor? It's been a minute since I've done this. I'm not lying. Oh, it's definitely not that. Okay. Okay, literally, how to do this is just you type in, you go to menu, okay? Sorry, I had to get to the bottom of this. This is annoying. Okay, yeah, you go to the bottom, or you go to menu, go to algebra, you go to factor. You type in that denominator, and you'll get a factored equation. That will be this. 4s squared plus 6s over 2 times 2s plus 3. I'm going to factor that. I'm sorry, I'm going to factor the numerator as well. The numerator is relatively easy. 4s plus 6 times s. That's the numerator. Does everybody agree with me on that? Sweet. Like I said, denominator, what it's going to come on your calculator is 2s plus 3 times s squared plus 3. Well, does anybody see what we could do here to maybe cancel some stuff out?
Divide that in half.
We could do that. I also just did 4s plus 6. What's up? Multiply that in. 4s plus 6 times s squared plus 3. Those cancel out. S over s squared plus 3. That's your answer. But did everybody see on your calculator how to factor that out? Sweet. Just factor, straight up factor.
Now this is a good algebra.
Menu, number,
Yes.
then
Yes, menu, algebra, and then factor. So if you want it in numbers, it's menu 3, 2.
So our part A answer is just that final matrix.
Yeah. This is part A's answer. That's part A's answer. This is part B's answer. Does that make sense? Yeah.
Wouldn't you have just done that like from the start, like from the original YTS, just cross out the 6 plus 4s and then just multiply by s by s?
You're totally right. He's very right. I could have just done this. Boom. I just did it the hard way. So you're thinking smarter, not harder. I like that. My bad. But yes, you could have done that. There's the factoring involved. I just want to show it for process sakes, right? Okay. Does that make sense? If for the people who got here a little late, if you want to take a photo of that, you're more than welcome to. I have this recorded, and it's going to be up on YouTube as soon as possible. Yes. I will talk to HKN people, and we will figure that out. But it'll be in the HKN teams for sure. I'm pretty sure it's as simple as just putting 2 videos together. I don't think it'd be that hard. So it should just be one. Yeah. I'll talk to them. All right. Okay. I got 3 more questions left. Does anybody have any questions with that thing? So on your homework, there was, what was it? It was like natural, it was system specifications. We did that with the first one. Network response, we just did that. And now we're about to do natural frequencies. Okay. So if you, I don't know if y'all are noticing, but it's a lot of similar math, just kind of structured at the end a little different. Are y'all seeing that? So, okay. Okay. Okay, I'm going to read this question out. excuse me. The zero-state S-domain network shown in Figure 2 uses a voltage-controlled current source as an active element. Use the component values given to identify and label the natural frequencies of the network with respect to open circuit and short circuit connections at A and B, or AB. Indicate the stability conditions for each connection. Be specific as to the condition of the stability. Okay. That I would suggest taking a photo for anybody. Does anybody have any idea of what we should do first? Anybody have any idea? Is this something maybe we do KVO, KCL, name? Is there something that's kind of, we need to add to the matrix, or not matrix? I kind of gave it away, but add to the question. I agree. Technically, it's just like a stand-in source. It's a variable source. We don't put an actual number to it. We just put the fact that it's there. So I'm going to put that. How would you recommend we polarize that current source? If that's so, would you say point the arrow up or down? You'd say down.
Up is positive, right? So up.
I like going up, so I'm gonna go up. Does anybody else? Would anybody else go down? It's totally fine with that, but it just mess up my math. No, does anybody have any issue with me going up? But okay. We're gonna go up, and we're literally just gonna call this JG of S. Fun. All right. So because we said JG of S, what should we do? Name, KVO, KCO. Name. Everybody agree? All right, cool. We're doing name. All right. So name involves what? Well, like what? What did you say? Huh? Thornton? No, that's how you use name to find Thorntons or Thevenins, not Nortons. Whatever. We need current sources and admittances. Okay. So what is the admittance in your first node? Anybody?
Oh, yeah, C1 and L3.
Okay. What is the admittance of C1?
Is it 1 over?
No. That's C1. That's all good. So what is the admittance of L3?
1 over.
Boom. 1 over SL3. Okay. Is there anything being shared between node 1 and node 2? Anybody? Do you agree with him? Okay. I agree. That's an L. Okay. 1 over SL3. That's negative. 1 over SL3. Okay. What are the admittances connected to your second mesh? Second node. Node. They're not meshes. They're nodes. Yep. Oh, yep. So what did we already write down that's also connected? 1 over SL3 plus G2 plus SC4. Y'all agree with that? Okay, this is nodal voltages. I gotta remember that. Equals. Okay, so then we have in the first matrix. I'm sorry, I keep saying matrix. In the first node, what do we have in terms of a source? What sources do we have? JGS. Positive or negative? Positive. If it was going down, it'd be what? There you go. JGS. All right. And the second mesh, what do we have? Negative what? GM V3 of S. I agree. All right. So V3 of S is what in terms of nodal voltages? V3 of S is right here with the polarity of positive on the left, negative on the right. I agree. VN1 minus VN2. I guess these are all S's, but whatever. Okay. Time to put them into the respective things. I'm just going to focus on this. I'm going to kind of skip some steps. Got any questions, let me know. I'm putting it in independent sources or areas. There are no dependent over here, so I don't need to do anything. Here, we said that V3 equals VN1 minus VN2. That's all multiplied by GM. So therefore, it's GM, negative GM. And the bottom, all multiplied by VN1 and VN2. Does that make sense? Yay, nay? That makes sense? Cool. All right. Moving on to the matrix itself. Or I guess the left side of that equation. All right. SC1 plus 1 over SL3, negative 1 over SL3, minus GM. This becomes 1 over SO3 plus G2 plus C or SC4 minus GM. That's not supposed to be a minus. That's supposed to. I have these polarity. Wait, hold on a second. Hey. I missed something. There is supposed to be a negative here. That is my bad. There's supposed to be a negative here, meaning there's the polarities of these flip, meaning that is positive and that is negative. That is my bad. So that becomes a plus and that stays a minus. Does everybody understand what I did there? I'm sorry for the confusion. Does that make sense? Okay, cool. Sorry about that.
Do you mind just explaining why?
So the direction of this current source is going to ground. So it is going away from the node, therefore it is negative. And so I have that negative GM VN3. Still VN1 and VN2 are the correct right there. VN1 minus VN2 based on the polarity of V3. Okay. So technically it'd be this. Negative GM times VN1 minus VN2, which would then be negative GM VN1 plus GM VN2. Does that make sense? Cool. All right. Yep, and that would, yep, okay, cool. Sorry about that. All right, and that equals JG of S and 0. Okay. Can anybody tell me what we need to do next? We have a matrix. Cool, yay, fun. What do we do with said matrix? Last problem, we found trans admittance. Okay. Does it say anything about what we want to find? No. Okay. So, do y'all remember how Russell found the natural frequencies? What he used? There is a specific. We found transimpedance in the last question. Okay. Would you say we do something similar? We do the exact same thing. Do something completely different. That's evidence. That's different. And technically, for this equation, JG of S is numericalist. It's just a variable. It's not really there. You said similar though. I agree with similar. Should we find trans admittance? Should we find that? Should we find trans admittance? Should we find some other type of impedance / admittance? Does anybody remember how for the homeworks y'all did that in terms of finding this stuff? No? Yes, maybe. It's been a while, I assume. It's also been a while for me, so this is weird to remember. So is that a no? Does anybody remember the phrase driving point something? No? Driving point impedance, driving point admittance? Nothing? No. Okay. That's a thing. For these questions, you're going to find driving point impedance or driving point admittance. Kind of a helpful cheat sheet. When you use MAME, okay, you will be finding your driving point admittance. Okay. When you use NAME, you will be finding your driving point impedance. That's simple. Okay. This is for natural. I'm going to tentatively say possibly because I do not know if you can. Essentially, I don't know if you could call this also driving point admittance. I don't know if you could. So that's what I'm saying. I don't know. But for this question, yes. And for questions I've seen before, you're finding admittance or impedance, whether it's called trans or driving point. It's different. That kind of doesn't matter in my mind of how to solve the equation. Now, probably there's some, actual reason to do that, or else I don't think Russell would do it. But yeah. So in this case, MAME, you're finding admittance. NAME, you're finding impedance. We're just going to say that. And in this case, it's driving point. We're just going to say that. Now, there's probably a definition of driving point impedance in a minute. Don't know what it is. We used what? MAME or NAME? We used MAME? We used NAME. I agree. So that means we're finding impedance or admittance based on what I just wrote. Admittance. Impedance. There we go. Cool. Okay. So, yeah. So that's it. So our driving point impedance equals that voltage AB over our JG of S. Okay. What is VAB? In terms of nodal voltages. Huh? V and 1? Does everybody agree with that? Yeah, it's V and 1. It's V and 1. So V and 1 over JG of S. Okay. Okay. So what is V and 1? In terms of Kramers. We have our V and 1 is just, or what do you call it? Our V and 1. Where's our V and 1? In our first node. Or technically also VAB. It's in the first node. So therefore, we're looking at our first node. What is our reference? Where is our reference? Why do you say node 2? That's not an independent. Node 2 has a dependent.
Oh, so triangle one.
Boom. It'd just be triangle 1, 1. Yep. So I'm going to say V and 1 is equal to negative 1, 1 plus 1, because this would be I plus J, which they're both 1 in this case, because you're looking for your nodal voltage 1, which is whatever. And then that's times delta 1, 1 over delta times JG of S. Well, that JG of S and that JG of S cancel out. Do y'all agree? Okay. So that means your driving point impedance is literally just delta 1, 1 over delta. Y'all agree? Yay, nay? Yay? Okay, cool. Don't let the negatives trip you up. You need to always remember this is here, especially when it's I is 1 or your I plus J equals 3. When that happens, you need to remember that negative will be there, and you need to put that negative tied to that. But since we have it's just 1 plus 1 equals 2, negative 1 to the 2 is just 1. So that in this case that does not matter. But don't let that trip you up. Sometimes that'll pop up to where there will be a negative. Okay. So delta 1, 1. What is delta 1, 1? How do you find what delta 1, 1 is? Yep. So what is that? Fun. Okay. Delta 1, 1 equals 1 over SL3 plus G2 plus SC4 minus GM. Y'all agree with me? Yay, nay? Yeah, nay? Okay, cool. All right. Delta as in the determinant. Would y'all put this in your calculator or would y'all do it by hand? Just general question. Hand? Anybody else? Yay, nay? Does anybody want to see how I do it by hand? It's messy, but I'll do it. It's sucky. I don't really remember how to do that. But I just remember it exists. I can figure it out and show you at some point. But y'all just want to see it by hand? I bet. Okay. So it is this. I'm going to erase that. It's this term multiplied by this term minus this term multiplied by that term. Do y'all agree? Bet. Okay. All right. SG1 plus 1 over SL3 times 1 over SL3 plus G2 plus SC4 minus GM. And that is all minus by negative 1 over SL. That's not that's whatever. L3, yes. Negative 1 over SL3 plus GM. All right. I like to do things in terms of factoring stuff out. So this one do that. What did I do? I did that. Okay. I like to go here to here, here to here, here to here, here to here, and then the SL3, whatever. Just factoring stuff in. So that just becomes SC1 over SL3 plus SC1 times G2 plus S squared C1 C4 minus SC1 GM. Did everybody see how I did that? Cool. All right. Now I got to multiply that one out. So that then becomes plus 1 over S squared L3 squared plus G2 SL3 plus SC4 over SL3 minus GM over SL3. Do y'all agree with that? Yay, nay? Yay, sure. Okay. Pretend everyone said yay. Okay, now I have to go to the next term. Just multiply this in. Let's multiply those out. Oh, I didn't want to do that. Whatever. Okay. So then that becomes, that is all minused by negative S, 1 over SL times negative 1 over SL just equals 1 over S squared L3 squared. And that becomes minus GM SL3. Okay. Can we cancel out any like terms? Short answer, yes. I will show you what we can cancel. This term is the same. You multiply that negative, they now cancel out. This term, the same. There's that negative, they cancel out. Negative times that, negative times that, positive, they have opposite signs. All right, so that means the entire determinant, SC1 over SC minus SC1G2 plus S squared C1C4 minus SC1GM plus G2 SL3 plus SC4 over SL3. Cool. All right. I don't like canceling out the S's, as in, I'm not going to do that. I'm not going to do that. The reason is so I know on every single fraction what to, like, every single fraction has an SL3. If I cancel that out, only ones, it might trip up my brain. So I just keep them there. If y'all want to cancel them, go for it. I don't care. What's up? Not yet. What I'm going to do is I'm going to now put everything back together. So your total driving point impedance becomes 1 over SL3 plus G2. That's a G. That's still a G, whatever. SC4 minus GM. That is the numerator. Denominator. SC1 over SL3 minus SC1 G2 plus S squared C1 C4 minus SL1 GM plus G2 over SL3 plus SC4 over SL3. Okay. Well, like I said, we have stuff with, a fraction. So I'm going to multiply the whole thing by 1. What is my 1 going to be? If that made sense. Oh, my drink's been there. SL3 over what? Yep, I agree. SL3. Boom. So that gets rid of that. We'll see how in just a sec. So SL3 times 1 over SL3 just gives me what? Boom. Just 1. So then that becomes SL3G2 plus S squared C4. I'm going to put the L3 first. C4 minus SL3GM. Then this gives me SC1 minus S squared L3C1 G2 plus S cubed C1 C4 plus S squared L3 L1 Give me 1 sec. That's not supposed to be an L1. That's supposed to be a C1. C1 GM. Yep, cool. Yep, okay, sorry. Then that becomes G2 plus SC4. Does everybody see how I did that? Okay. Now I'm going to group like terms. Or I'm going to put everything to the highest order and also group like terms. Numerator. SL3, I'm sorry. L3C4. We're going to do plus SL3 G2 minus GM plus 1. Does everybody see how I got that? Yay, nay? Cool. Yes. Okay. All right. Then why am I having that as a? Okay, cool. We're good. All right. S cubed C1 C4 plus S squared L3 C1. The reason I have that here and here. I don't know why I did that as a negative. It's supposed to be positive. I made a mistake here. This first term is supposed to be S over SL3 plus SC1 G2. I made a mistake up there. I'm sorry. So where right here, that's a positive, and now that is a positive right there. That is my bad. Does everybody see where I made my mistake? Okay. In my what is that called? Determinant. Sorry. When I was multiplying these out, this times this and this here, I accidentally put a negative here. I put a negative here. It's supposed to be positive. So that means right here, that's now positive, and now that is positive, and so that is positive. That's my mistake. Do I need to go over that again, or does that make sense? You sure? Okay, cool. Everybody else, we're good? Okay. Did everybody see where I made that mistake? That was literally on accident. Oh, my bad. Okay, so like I said, I have that S squared L3C1. I have that term and that term, so therefore I can just do a G2 minus GM because I grouped the like terms. Y'all see how I did that? Y'all see how I did that? Yeah. Here? You are correct. Yeah, that's my bad. Instead of being like me, y'all could use your calculators. So there's less mistakes because obviously I'm making a lot. Okay, cool. We got that. Now I'm going to go on to the terms with just an S, which is here and here. So then that just becomes S plus, I'm sorry, that's not plus, S C1 plus C4. And then a term without an S just becomes G2. Okay. Does anybody have any idea of what we should do next? We have it in terms of highest forms of S's. What do we need to do with those highest forms of S? Normalize it. So to do that, we need to kind of divide out everything. So ZDP, we'll take out an L3C4 on the numerator and L3C1C4 on the denominator. Does everybody see why? Does everybody see why? This term is multiplied by that, so we have to take it out. The highest form of S is also multiplied by L3C1C4. Take it out. So that'll become our K. But if you also notice, boom, 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 just 1 over C1. So then we have an S squared plus S. I'm going to do this. SL3 times G2 minus GM. This gets kind of ugly. Sorry. It just happens. That becomes then an L3 C4. Does everybody see why? We took out the L3 C4 from that equation. If we were to multiply that back in to get this number here, we'd have to then multiply it out again here to get this term here. So therefore, we divide this number by the L3C4. Does that make sense? Yay or nay? Questions? Does everybody see why? If I multiply this L3C4 to this number, that L3C4 is going to cancel out this one. That'll just let me with that term. Does that make sense? Yes? Still, I got some.
Added that L3C4 on the bottom for the SO3 G2 when it was GM.
I don't. What are you saying? I'm sorry.
You factored out the L3C4
Correct.
and the S2.
Yes.
But in order to factor that out,
Correct.
you need to have that.
Correct. Correct. So then I'm about to do the same thing with the next term. 1 over L3C4. Because then if I multiplied the L3C4 times the 1 over L3C4, I would just get 1, which I would need to get. Does that make sense? Yes? Is this looking familiar to any? Is this looking familiar for y'all? Cool. All right. Same thing to the denominator, just a little more messy. Okay, L3, or S to the third. We understand why that. We factored out the L3C1, C4, right? Okay. All right. So then that becomes plus S squared. I'm going to do that a little differently. No, I'm not. L3C1, G2 minus GM over L3C1, C4. Y'all see why? Cool. Plus S times C1 plus C4 divided by L3 C1 C4 plus G2 L3 C1 C4. Okay. Did that make sense? We're done with the hardest part. Now plug everything in your calculator. But does everybody see how I got to this point? Now, obviously, like I said, I made some mistakes. So you could do two things. You could try to get good at this process and try to make as minimal mistakes as possible, or you could put it in your calculator. Putting it in the calculator gets you a form you don't love. For me, this has always been kind of easier because I can see the step-by-step process of how I get to each point, and also more partial credit. You put it in your calculator. If it's wrong, it's wrong. I don't know how your TA is going to work this semester. I really don't. Have they been gracious on y'all's problem sets? Never mind. So yeah, I don't know how that's going to go, but more partial credit is always nice. So for me, the more steps made sense. Yeah, but if y'all find out a process that works for y'all, don't hesitate to do that. So now I'm literally just going to plug every value in to the equations. And like I said, I just did that for my calculator. Y'all remember how to do that? Store variables and put all that stuff in. Do people know how to do that? If not, come see me afterwards. I can show you how to do it. It's pretty easy. 2. Now, like I said, plug in numerical values. Yeah. So like what I do is I plug in I put in the numerical values for everything, and then I literally just type out this equation.
Oh, so you figured out what K was. That's the one time that you plugged in everything else.
Yeah. So then that becomes S squared plus 1 over 4 times S plus 1/2. These numbers are also really easy. I like to do things as variables. You can put numbers in. It might make your life a little bit easier. Do whatever works for you. Okay, that's the numerator. Denominator becomes S cubed plus 1 over 4S squared plus 3 halves. That's 3S. 3 halves S plus 3/4. Okay. So, can anybody tell me what we do next? We are trying to find the open circuit and short circuit natural frequencies. Anybody tell me what to do next? Yay, nay, maybe. Yes. Yes.
Oh, so think the quadratic?
I mean, you can do the quadratic formula, but everybody get out your calculator. That'll make your life a lot easier. So we want to find the roots of the numerator and the denominator. Okay. So go to algebra, menu algebra. Okay. Polynomial tools, and then complex roots of polynomials. When you type that in, you should get the function of this. C poly roots, and then this. So if I want to find basically the roots of the denominator at one point and the roots of the denominator as a second point. Okay, I want to find both of them. I like to do them individually because it just makes sense. So literally, I'll do this. I'm going to show you what to type in your calculator. S squared plus 1 over 4s plus 1/2. You need to add a comma, put an s. So that'll tell the calculator, oh, I'm looking for the roots of s. That's it. Same thing with the denominator. So it would be s cubed plus 1/4 s squared plus 3/2 halves s plus 3/4. And then that same comma s. Okay. So that'll get you your straight up roots. But the roots are the opposite signs to what your equation's going to be, right? Because you put it in the s and it's just going to make your equation 0. So then CDP equals 1 over 2 s plus, and you want to do the complex one because you never know if something's going to be something plus j. You never know when it's going to happen. And if there's no j, it'll still give you a real number in terms of if you put in the C poly. So it becomes s plus 1 or 0.125 plus j 0.696. And then the second one becomes s plus 0.125 minus j 0.696. 696. That is the numerator. The denominator is going to have 3 zeros. S plus 0.468. 468, that is an 8. Okay, this one then becomes S minus 0.109 plus J 1.261. And then S minus 0.109 minus J 1.261. So that is those equations. Now, we want to find what our open circuit and short circuit natural frequencies are. Okay. Can anybody tell me what is what in terms of where you would find your open circuit natural frequencies and short circuit natural frequencies? We have a numerator and a denominator. Can anybody tell me which holds what? Why do you say that? Okay. We'll blow your mind. ZDP, or Z. V over I, right? Y'all agree? So essentially what we found are zeros in both the numerator and the denominator. Y'all agree with that, right? Okay. Well, in terms of this here, if we had a 0 in the denominator, if we had a 0 in the numerator, what does that mean? We have a voltage in the numerator. If we make it 0, we have what? How much voltage do we have then? If we have a 0 in the numerator, which is voltage, what would be our voltage level? 0. What is 0 voltage? Short circuit. Okay. When you have in terms of impedance, I is in the denominator. When we have a 0 in the denominator, our equation becomes what? Mathematically, what is 1 over 0? What is anything over 0? Undefined, technically infinity, right? Technically infinity. What is infinity in terms of impedance? Open circuit. That easy. So, for impedance, it's voltage over current. If we have 0 voltage, we have a short circuit. If we have 0 current, we have an open circuit. Therefore, if we have a 0 in the numerator, or the zeros in the numerator are your short circuit natural frequencies. The zeros in the denominator are your open circuit natural frequencies. Now, that is for impedance. What would it be if it's admittance? Opposite. Does that make sense? Does that make sense? Cool. All right. So that means our numerator has our short circuit natural frequencies, and our denominator has our open circuit natural frequencies. Now, Yeah, I'm gonna write those out, and then we'll overall. I wouldn't say resistivity. The driving point impedance is the overall impedance of the circuit, and the driving point admittance is the overall admittance of your circuit. I believe. To the opposite of impedance. No, because impedance is a complex number. Resistance is a real number. Resistivity is the real part of impedance.
No, but like in theory, impedance is if you add up the quote unquote resistivity of all components, like capacitors, inductors.
I guess, yeah, I guess that's one way to look at it. That's one way to look at it. So, like I said, I'm going to write down the short circuit and open circuit natural frequencies. So I'm going to write the short circuit down. Okay, that is negative 0.125 plus or minus J 0.696, and that's all in radians per second. I should ask that, whatever. Open circuit equals negative 0.468, comma, 0.109 plus or minus, well, plus and minus, I guess, 1.261 rads per sec. Okay, so we're almost done. We're almost done with this equation, or with this question. All right, I'm going to wait till everybody has that down. That's just a comma. Sorry, that's just a comma. All right. All right, I'm going to go back up to the top. Is that all right? Okay. So we have determined our short circuit, our open circuit and short circuit natural frequencies. We have determined that. I'm sorry. Well, the natural frequencies are with respect to open circuit and short circuit connections. Okay. We have to be specific for the stability conditions of each connection. Okay. So stability is found in the denominator. Okay. So if you want to find if your short circuit is stable or unstable, put it in the denominator. Same thing with the open circuit. Just make that the thing. No. Just in general. Wherever your short circuit, well, I'm actually gonna hold off on what I just said. Yes, what I said is correct, but don't think of it that way yet. Stability. Okay, you have a graph. Okay, literally, if you have anything over here, it's stable. One thing over here, unstable. Literally, just one thing can screw it up. But what defines stability is the poles of a function. The poles of a function. Where are the poles of a function for like a fraction? If there's a fraction in terms of the numerator or the denominator, where are the poles? In the denominator? Yes, I agree. This is a good way to think of it. A zero, what is it? A zero is in the numerator, right? Because it's literally a zero, it just becomes a whole. There's nothing there. Okay. Denominator, if there's a zero in the denominator, you got infinity. What's infinity? A giant pole. So it's a pole. That's how that literally nomenclature came. So you want to think of it of when stuff is in the numerator or the denominator. You want to think of it that way. So, like I said, anything over here, anything in the left, this is called the left half plane, this is called the right half plane. Literally just separate a graph into left and right. That's it. If everything in if all of your roots are in the left, stable. Literally just one in the right, unstable. Literally just one. So here, and that's why I said denominator, because usually your poles are found in the denominator, but you don't have to specifically put it in a denominator. I can find, hey, are these both negative or positive? Are these if these are both negative or positive? I can find out if it's on the left or right. And also, I want to say this. This is a real and imaginary graph. Your imaginary is your y-axis. Your real is your x. Okay. First question, or first roots, better word. You have negative 0.25, or I'm sorry, 0.125 plus or minus 0.696. What is that? Is that positive, negative? Is it on the left? Is it on the right? Are they both on the left? Okay, cool. Stable. That easy. Okay. This number here is negative, left or right? Okay. These two numbers, are they positive or negative? They're both on the right. Does that mean they're unstable or stable? I agree. That easy. Does that make sense? Yes? Cool. Any questions with this one? No? Sweet. All right. Give me just a sec. And then, yeah. So that was your first homework. Those 3 questions were your first homework. That was it. So now I got to do stuff on your second homework. Thevenins and Nortons and op amps. Gotta hit op amps. Y'all, he did op amps my semester. He did the semester after at op amps. For some reason, he dropped op amps last semester, and now he put back op amps this semester. I don't know. I don't care. Russell does Russell. But yeah, so this is the Norton's problem. It's pretty easy because it says it. The current-driven network shown in Figure 47 contains a voltage-controlled voltage source and a collection of resistors. Derive the Norton's equivalent network at terminals A and B for this network. Express components for the Norton's equivalent in numerical form using values and on the schematic. Can anybody tell me what we should do? Yeah. Yes, I would agree with that. So I'm just going to write this down. Norton's main Thevenin's. I'm just going to write it like that. I don't want to write the full word. Name. How I think about it. Norton's can't be named because there's 2 N's. Make sure there's only 1 N when you think about it. Because Norton's name, there's only 1 N. Thevenin's name, only 1 N. That's how I think about it. It's kind of simple and easy. All right. So, like we said, MAME. Okay. Well, we have some issues, in my opinion. Would anybody agree with the issues that I see? Anybody see any issues? Yeah. How do we change that? Well, it's in parallel with the resistor right now, but we can do what to get that? We do a source transformation. I'm just going to say that. And we do resistor R1, 100K, plus minus. What is this? 100K? Well, we need EG of S, which equals that 1 milliamp. What do we do next? 1 milliamp. How do you get voltage from a current and voltage? V equals I times R. Boom. We have that current of 1 milliamps times that resistance of 100K. Therefore, we have a value of 100 volts. Does everybody agree with me on that? Everybody see how I do that? Does the polarity of how I did that make sense? Like, do y'all care about that? Well, that polarity has to be that polarity. Does that make sense? Basically, arrow pointing up, positive on the top. That's how I think about it. So I'm going to do MAME, which, as we said before, everybody likes to do clockwise. Therefore, I'm going to do that. We got this one right here. What else do we do in Norton's and Thevenin's? We kind of have an open circuit, but what should I do there? Something involving a source and maybe put a numerical value on it that's kind of low. Why would you say current before MAME? Voltage source. Yeah. Voltage sources and resistances or impedances are what we do for MAME. Does anybody have any idea what we do next? Maybe put a voltage source of, say, 1 volt. Yay, nay. Okay, I'm just going to do that. All right. I'm going to put that between A and B. I'm going to put this in this rotation. Does anybody have a suggestion? I'm going to do it one way, but does anybody have any suggestion of how that polarity should be? Because we put this source here. We put this source of E naught of S equals 1 volt. We put that there. We can figure out how it goes. But you want it up? I'm going to be honest. I'm going to do a flip. because I just want it in the same direction as the current. So I'm going to have it like that. That's how I'm going to do it. Now, you need to remember how you put the polarity of your source in terms of how it's going to end up at the end. So I have my voltage source pointing down. My polarity is going to ground. So therefore, I want my, what's going towards B. Therefore, I want my my source, my Norton's equivalent source at the end to point towards B. Does that make sense? If we're to point it towards A, we need to keep it in that function, or that way. All right. So I'm going to do name. Oh, this is a 3 matrix. This is fun. This is really one of the only times, Norton's and Thevenin's are kind of the only times you're going to see a matrix bigger than 2 by 2s, because he usually makes it relatively easy on it. So I'm going to do this real quick. All right. In variable notation. So the impedances, well, this is all resistances, so I'm going to say resistances. The resistances in mesh 1 are R1 plus R2. Is there anything being shared with IM1 and IM2? No? Yes? Nope, I agree. Anything with 1 and 3? Yay? Nay? Nope, I agree. Same thing here. Literally at keep them. All right. Mesh 2 has R3 plus R4 plus R5. Anything being shared between mesh 2 and 3? What are those resistances or resistors or whatever they're called?
R3.
Yep. So are they positive or negative? They're being shared. Yep. Negative R3 minus R4. Copy paste here. That's supposed to be a minus. I will make that better. All right. And then stuff in IM3 is just R3 plus R4. What is in, what are these sources in mesh 1? Okay. What is the polarity of mu VA, mu B, VB? I agree. VA minus VB. All right. Now, what is is there anything in mesh 2? Mu A, yep, I agree. And then, what is it in mesh 3? Is there anything in mesh 3? The source we put in? Would it be positive or would it be negative based on the current direction? Positive or negative? The direction of current is going this way, which is also going out the same polarity. So therefore, it is positive. Now you see why I put the polarity of that source that way. It just makes sense in my brain. It was easier. All right. So we're going to... Okay. What is VA in terms of currents? We have a resistor in mesh 1 that is, I'm sorry, the VA is the voltage on that resistor in terms of mesh currents. What is times what? Yeah. That's him. I gave that away. All right. What is VB? VB is here. With IM2 going that way and IM3 going that way. IM2 is going into the positive part and IM3 is going into the negative. You said R4 times. I agree there. Other way around, I'm sorry. It's going into the positive part of VB. IM2 is going into the positive. IM3 is going to the negative. Therefore, IM2 minus IM3. I also forgot to mention about VA. Is it positive or is it negative? We said that it's R1 times IM1. But the polarity is going into the negative of VA. Therefore, it is positive or negative? Negative. I agree. That's important.
So
All right. I'm just going to do with this one right here, but I'm going to keep everything, or I'm going to do independent, what we put in, and dependent sections. All right. So EG of S 0, 0 plus 0, 0 E naught of S. We agree with that so far? Yay, nay? Cool. Sweet. All right. Now I'm going to put everything together. So then we have a mu, negative mu times VA, which is negative R1 times IM1. I'm going to make that a bracket. IM1 minus R4 times IM1 minus IM2. Does everybody agree with that? Does everybody agree with how I did that? Yeah? Sweet. Yeah, okay. Same thing here, except the mu is positive. Mu times R1, or negative R1, IM1, minus R4 times IM1 minus IM2. And that is 0 on the bottom. All right. So now I'm going to separate those into, like, I'm going to take out the IM1s and everything like that. So then that becomes, if I have a negative times a negative, that becomes then positive. Mu R1, negative times a negative is a positive. Mu R4, negative times a negative gives me a negative. Negative mu IM2. Does everybody see how I did that? Okay. The next row is literally the same, just flipped polarity. 1, negative mu R4, mu, that's not supposed to be IM2, that's supposed to be R4. Yep. Yep. Cool. And then the bottom row is just 0. IM1, IM2, IM3. That is technically all being added by this term here. I just left it out. Does everybody see how I did that? Cool. All right. All right. So now then I want to subtract that over to the other side. All right. That becomes R1 plus R2 minus mu R1, negative mu R1, and then mu R4. That's not supposed to be R1. That's supposed to be R4. Sorry. All right. Mu R4 there. R3 plus R4 plus R5 plus mu R4. And then negative R3, negative R3 minus R4 minus mu R4. That's 0 here. This is negative R3, negative R4, R3 plus R4. And that is all multiplied by IM1, IM2, IM3. And that is this thing here, this vector, I think is what it technically is. 0, 0 plus 0, 0, I, or E naught. Does everybody understand how I did that? Yay? Nay? Cool. All right. When you put the numerical values into the matrix, that then becomes this. Negative 200 times 10 to the third minus 4 times 10 to the third. 4 times 10 to the third. Also, if you haven't noticed, I have my calculator in what notation? Yeah, engineering. So that's how I like to do things. Just kept them there. 400 times 10 to the third goes there. 8 times 10 to the third. 6 times 10 to the third. 0. Negative 2 times 10 to the third. And then 2 times 10 to the third. And that is all multiplied by IM1, IM2, IM3, and that equals, what the, 100, 0, 0, plus 0, 0, 1. Okay. We need to find two things. What do we need to find? We need to find an equivalent source and equivalent resistive or admitted? Whatever. Either resistor or conductor. Can anybody tell me what we're going to find in terms of either a voltage source or current source or a resistor or conductor? Yay? Nay? No? No? we're going to find a current source and a conductor. That's what we're finding. Technically, an emitter, if you want to say that. That sounds weird. But yeah. So the process of Thevenins and Nortons, you kind of turn off one source, keep the other one on, then turn off the other source, put on the other one. Does that make sense? Y'all kind of remember that? Okay. So for here, to find the current source, Jn, we will find that third, or IM3, when E naught is equal to 0. Does everybody know why? To find the source, you find whatever node or mesh your terminals are in. And in this case, our terminals, A and B, are in mesh what? When E naught is 0, the source we put in. But does everybody understand why I said IM3? Our terminals are A and B are in IM3. Therefore, I'm looking for the current in IM3. And we just do it when E naught is 0. So basically, this matrix here is nothing. This doesn't exist. And so you then do, I don't know if y'all know how to do this, but what I do is you can do REF, but how I put in my calculator is I'm going to call this Z, I, VI, and VD. Okay? What I do is I say my I vector equals my Z to the -1 vector times my VI vector. Literally just put that in your calculator. Has anybody ever done that before? How do y'all usually define the matrix? Is it RREF or REF?
RR.
Is that reduced row echelon form? Okay. Has anybody ever done it this way? Whatever way y'all are comfortable with, do it. But this is how I do it. It makes sense in my mind because it's literally you're technically dividing your voltage matrix by your impedance matrix. But in this case, you can't divide matrices, so you can multiply your voltage matrix by the inverse of your impedance matrix. So that works for me. So in this case, after I put in all the values, my mesh currents become IM1, IM2, IM3 equals negative 0.5, 100, and 100 milliamps. So what is J of N, or Jn? At E naught, or when, I'm sorry, when E naught is equal to 0. I never fully finished that. That's my bad. Did that make sense, though? Okay, cool. My bad. Well, IM3 is 100 milliamps. What does that mean? Yeah. So that means our Norton equivalent source is 100 milliamps. So now, what do you call it? We can't just get admittance from current, right? But we can still use that and divide it by something. What do we divide it by? To find our, I'm just going to say emitter. I don't know if that's actually the word for it, but whatever. It's the admittance element. You're finding. What did I write down? Where did I write it down? I didn't write it down. Here. When you use yes, technically, but what we're doing is we're using our current, our mesh current, divided by that source, which we put in a voltage source. Well, we kind of want to get rid of that source in terms of that source is 1. I can't explain why we get admittance. It's just current over voltage. that is literally the definition of admittance or conductance. But in terms of how we just get here in the math, what's up? Conductance is the real part of admittance, and then the imaginary is called susceptance. It's a B. I don't know, but in this area, we take our current, divide it by that source we put in. Okay, we put it that's how you find your admittance. When I'll put it this way: we are finding Norton's equivalence, which is using MAME. Which is using MAME. What am I saying? It's using MAME. It's using MAME. We used MAME. Oh, what am I saying? You do find, when you're using MAME, you're going to find your impedance. When you're using MAME, you find your, let me write this down. MAME is going to give you admittance. It's going to give you admittance. NAME is going to give you impedance. It is literally because of this, to where you're using sources with MAME that are voltage sources. When you put those on the numerator, or numerator doesn't really do anything. When you put it on the denominator, you get admittance. No. When you're using MAME, you find admittance. You find admittance.
But you use it with MAME, you use impedance.
Yes. Yes, you use your impedance matrix to then find your admittance. Same thing with NAME, or vice versa with NAME. You use your admittance to find your impedance. I hate that these words are so similar. Whatever. Does that make sense? Kind of? Okay, cool. I'm going to leave that there. I'm actually going to move it down a little bit. Okay. So for our Norton's equivalent admittance, we use our mesh current 3 divided by our E naught when EG of S is 0. What is E naught? What value did we use for E naught? Exactly. So that's literally just M3. So when you put those in a calculator, IM1, IM2, IM3 equals 10, negative 500, and 0. Technically, this is milliamps, or microamps. I'm sorry. This is in microamps. But you divide that by our voltage of 1, and you get technically micro Siemens. But IM3 is what? So we have no conductance. I don't know. I think he wants this drawn out. I usually draw it out regardless. So we have A, then we have an admitter, I guess. And remember how we drew the voltage source facing B? I'm doing the same thing with our equivalent current source. If I popped it up, if I would have faced it towards A, I would have put the arrow towards A, but I did not. So that means Y of N equals 0. J of N equals, what do we say, 100 milliamps. And it's important to denote the polarity because if I were to flip the polarity going up, what do you call it? I would have a different polarity. As in, if my arrow would be going up, my J of N would be negative 100 milliamps. So it's important to denote those polarities. So, any questions with this one? All right. Cool. All right. Save the best till last. This one sucks. Yeah, op amps, not my forte. This problem is just a lot of algebra. It kind of makes sense. I really don't know how much Russell has gone over for op amps. The one question I have is, I'll get to that. But op amps are annoying. Op amps are annoying. I'll tell you that. I'll let y'all take a photo of this. All right. Okay. So I'm going to read this. What's up? Okay. We got one more. And this is going to be recorded so you can watch it again. I'm sorry, it is recorded so you can watch it again. And also, with the previous two semesters I tutored this. The first semester I did this, so a year ago, he had op amps. So that one's going to have two op amp examples. Last year's is not. Last semester's is not. So yeah, they kind of suck. So my fall 24 review is going to have two op amp problems. I think I do them literally first. And my spring 25 is not going to have any op amps because they did not have op amps on their test. So yeah. Okay, so let me read this. So an LM308 Generation 2 operational amplifier is being used in the non-inverting gain amplifier configuration above in Figure 1A. The frequency-dependent near-ideal level 1 model for this op-amp is shown in Figure 1B. The op-amp's open-loop voltage gain of G-vol of S is defined as a two-pole function right below. So we have the G-vol of S is equal to G-vol of 0 over 1 plus S over, that's omega P1, times 1 over S, times 1 plus S over omega P2. Those are just poles. Where he gives us values in this, where G-vol of 0 is 175K volts per volt. Omega P1 is 2 pi times 12 radians per second. And omega P2 is 2 pi times 1.5 mega radians per second. So those are just values. Derive the expression for the closed loop voltage gain V in I of S for this configuration defined as this, where V in I of S is equal to VO of S over EG of S, as in the output voltage over our input voltage, which is also equal to K in ds. N of S over D of S. From this expression, calculate the values of the closed loop and poles and express them in numerical form of hertz. Did I do that? I did not. Show your work in detail and all assumptions you make. Well, in detail, all assumptions you make, whatever. So we have an op amp there. If you also see, we have a circuit with an op amp here, but here we kind of have a way to model that op amp. Does that make sense? Kind of. Okay. I'm about to start drawing stuff and we'll see what happens. Okay. So we have, all right. We have that EG of S going to ground. This then becomes VP. This then becomes VN. That is positive. That is negative. Delta V of S. Okay. This then goes to a capacitor, which then goes to ground, tied to a resistor. That goes to my output voltage, V out. Yes, V out. Okay. But also, I have this voltage source here that I can tie to my output voltage. So that is technically this. Like I said, this kind of sucks. That's going to ground. G vol times delta V of S. So I basically replaced this op amp here with this model here, where the output is basically touching that V out of S. Also, this is positive up here, and that's negative. The output voltage, it's touching that. It's also going to ground. But I also have this delta V of S, which is the difference between VP and V negative, or V positive and V negative. Does that kind of make sense? Kind of. There's some materials that he has that kind of go more in depth on that. Your best bet to do with op amps is try to redraw the circuit in the equivalent circuit. And if it might take y'all a second, but that is how you'll really succeed at op amps. That's the best way to do it. It sucks, but if you get a little decent at it, do some more practice on it, you'll get some. Did y'all do that on the homework at all? But like, did y'all draw in the equivalent circuits? Yeah. So that's kind of clicking, kind of making sense. Okay. I would heavily look in his materials and look at those, because he gave you all the solutions, right, for your second homework. Look at those. Definitely look them over. Okay. So I'm going to start with this is just kind of, I don't know if I'd say basic, but I feel like this is something Russell goes over every semester. You can tell me if this looks familiar or not. Your output voltage equals your voltage gain times your delta V of S, as in your change in voltage between your positive and your negative rail. Does that make sense? Does that look familiar to anybody? No? Yes? Maybe? No, does it actually? Is it? It does? Okay. If not, trust me, because that is, we'll get there. We'll get there. So, like I said, the delta V of S is literally just the difference of the positive and negative terminals of the op amp. Does that kind of make sense where it's at? We're here. It's literally just the difference of the positive and the negative rail. No. We kind of find what the voltages are at both points. What's the voltage at VP? Oh, wait, I'm sorry. I needed to draw that in. Yep, I agree there. This one's a little harder to see. What is the voltage on this negative, this VM? It's tied to something. The capacitor. Would you say it's the capacitor voltage? Okay. So what is the voltage across that capacitor? It's kind of tricky. I could have also drawn this like this. Let's see if this works any better. I'll just put that. It's technically, it's the voltage across this capacitor with respect to that output voltage. Can y'all kind of see that and how I did that? The redrawing of that redrawing? It's kind of annoying. Like I said, it takes a sec. I'm going to go back to the other drawing, though, because I like my VP and my VNs right next to each other. So let's see if I can see how much I can tap. There we go. I just kind of like it right there. But it is how I drew it like that, it shows you that it's just the voltage on the capacitor with respect to the output voltage. So therefore, we're going to take the voltage division, 1 over SCF, because we're doing voltage division. We want to find the voltage across that capacitor. And for voltage division, we use usually impedances. Therefore, we would use the voltage, the impedance of the element we want on top over the total impedance in that branch. Did that make sense? Okay, well, I'm also going to write it out. So it's the voltage of the component we want, or it's the impedance of the component we want on top, 1 over SC4, 1 over SCF, sorry. And then on the denominator, it's the total impedance of that branch, which is 1 over SCF plus RF times VO. Is that making a little bit more sense now that I have it written out in terms of voltage division? So, huh? Oh, it's gonna happen. But in terms of that, I don't know. What were you saying? I'm sorry. So I'm finding the voltage across this capacitor. Okay, the voltage across this capacitor is just the voltage division with respect to V out. Now, voltage division, it's the impedance of the element we want on top over the total impedance in that line, as in CF and RF, right? And then you times the voltage with respect to, which is just V out. Is that making a little bit of sense?
Yeah.
That makes it, okay, cool. So we have that. Now I can plug it back in to the equation I just put earlier, which is this. So that means V out equals G vol of S times EG of S minus, because remember it's VP minus V in, sorry, minus, one other thing. this whole thing simplifies to this. 1 over 1 plus SRF CF times V out of S. Just makes it easy. I didn't want to think about it. I did not do that in my head. I got that from Russell, but literally plug it into a calculator, you'll get the same value. So it makes sense. So that becomes then EG of S minus 1 over 1 plus SRF CF times V out of S. Okay. Now I'm going to multiply out, or multiply in, the G vol of S. So V out of S equals G vol of S times EG of S minus G vol of S times V out of S over 1 plus SRF CF. Now I'm going to subtract, or I guess add this over to get V out of S by itself. I'll show you why in a sec. So now I'll have V out of S plus G vol V out of S over 1 plus SRF CF equals to G vol of S EG of S, which that means then we have V out of S times 1 plus G vol of S, 1 plus SRF CF times G vol of S EG of S. Okay. I'm then just going to get V out by itself. So divide over. I will show you why in just a sec. Of S, EG of S, divided by 1 plus G vol of S over 1 plus SRF. I don't have 15. Oh, I'm actually almost done. RF. Oh, yeah. Yeah. Get there about 8:45. Because sometimes he lets y'all start early. I don't know if Wednesday's going to be one of those days, but get there a little early. All right. So that is V out by itself. Does anybody know why I did that? It involves equations we talked about earlier from the question.
That's in the final formula is G vol of S times
EG of S. Yeah. The reason why is, I'm going to scroll up real quick. We have this here. Well, we found V out of S. Let me plug it into that equation. Is that making a little bit of sense? You use another equation to find that equation. It's kind of sucky. So like I said, the GV NI of S, whatever, equals V out of S over EG of S. Okay. Also, there's a form. I'm going to go back to the top again. This form here, okay? These two forms. 1 plus S over omega. Okay? It's just a form. I'm going to make this like that. To where I have 1 plus, well, actually, technically, this bottom part, I'm sorry. To where I have a 1 over, or 1 plus S over something. And I'm going to make that something called omega F, 1 over R F C F. Just kind of makes it easy. It's where I can do this. GVNI of S equals G vol of S times EG of S over 1 plus G vol of S over 1 plus S over omega F. Now, if I plug in the 1 over RF times CF into the omega F, I get this back. because it then becomes S over 1 over RF CF, which just equals to SRF CF. Can y'all see that? Does that make sense? It just kind of makes it easy in terms of the math. So I saw that from Russell, and honestly, I was like, I'm going to do that. That makes it easy. Okay, that is all over EG of S. What can we do? We have an EGS on the numerator, and we have EG of S on the denominator. What can we do? Boom, cancel it out. I didn't really want to read draw it. I'm sorry. Okay. So we have a equation for our closed loop voltage gain. Okay. In that, we have a variable that is our open loop voltage gain. Well, do we have something that equivalates to our open loop voltage gain?
Yes.
We do. It's right here. So then, just plug it in. It's going to get messy. So GVNI of S equals, I'm plugging that giant equation into here, right there. G vol of 0 over 1 plus S over omega P 1 times 1 plus S over omega P2. That's the first part. Denominator gets annoying. 1 plus G vol of 0 I'm going to do this, and then if it doesn't make sense, I'll talk about it. 1 plus S over omega P1 times 1 plus S over omega P2 times 1 plus S over omega F. That's it. We're not done with the equation. I'm just saying that's that. Okay. The reason yes, that's it. The reason I did that, okay, I could put, technically it's G vol of S over 1 plus S over omega P1 times 1 plus S over omega P2 over the 1 plus S over omega P or omega F. Omega F, yeah. But this is just going to, these terms are just going to drop down. Does that make sense? In terms of in the denominator. So I was like, I'm not going to do that. All right. We're almost done. Kind of. So it's still like we're finding the holes and poles of this. So that's our eventual end goal. I basically put this in a calculator, and by I mean Russell, and found the simplified form. Even it can. You're not putting anything in numerical form. Literally just put it in a variable. So like you'd have, like maybe you put a G for the variable of G vol of 0. And you put S obviously there. Also, you need to actually multiply. If you're doing like a C-solve or whatever, you can't just do S4. You have to do S times 4. I don't know if that was an issue. But yeah, you could just put this as like a G, that is an omega P1, or like a WP1, WP2, same thing here, WPF, and it's going to give you a simplified form like this. 1 plus S over omega F times G vol, that's a G of S, all over 1 plus S over omega P1 times 1 plus S over omega P2 times 1 plus S over omega F, all added by G vol of S. Is there anything in this equation that we have, minus the S, don't think of the S, that we do not have a numerical form for? as in this omega f is just 1 over RF times CF, and we have numerical values for that. We have a numerical value for G-vol of 0. That's not supposed to be of S. That's supposed to be of 0. We have numerical values for omega P1 and omega P2. Plug everything in. So when I do that, I get a numerator of this 6.825 times S plus 25.641 times 10 to the third. You technically could put the entire fraction into your calculator. How I did it is I separated the numerator and the denominator, so it's going to be a little weird how I do it, but you could do it differently. And then the denominator becomes 54.882 times 10 to the negative 15th S cubed plus 518.665 times 10 to the negative 9th S squared plus 13.302 times 10 to the third S plus 175 times 10 to the third. Yep. That's that. Now we want to normalize the denominator. Like I said, you could have done that earlier. I did not. That's just how I did this. And so I take out the 54.882 times 10 to the negative 15th. And I get a K of 6.825 divided by 54.882 times 10 to the negative 15th. And that is all multiplied by the numerator of S plus 25.641 times 10 to the third. Denominator, we have an S cubed plus 9.45 times 10 to the sixth S squared plus 242.374 times 10 to the ninth S plus 3.187 times 10 to the 18th. And now all you do is you find your holes and poles. So you'll have G, V, and I of S is equal to the K of 124.357 times 10 to the 12th. That's the K. The numerator in this case is S. Oh, it's still the same. 25.641 times 10 to the third. The denominator becomes S plus 9.6 times 10 to the sixth. Yep. Times S minus 5.004 times 10 to the third plus J 580.538. It's good. 9.46. Right there, times 10 to the third times S minus 5.004 times 10 to the third minus J 580.538 times 10 to the, well, I'm getting into that. Sorry. 10 to the third times 10 to the third. So what the question is asking, I'll get back to that in just a sec, is the values for closed loop, which we found, and the poles. Okay? And it's set in hertz. I forgot to do that. Mine are in radians per second. How do you get hertz from radians per second? involves 2 pi. I'm not going to lie. I do not remember at the moment, and that's bad. But you either multiply or divide by 2 pi. Does anybody remember anything specifically? No? Okay. Whatever. Look it up. Well, you know what? I got a freaking laptop in front of me. Let's figure this out. Divide by 2 pi to get from hurt. So, yep. There you go. Cool. Sorry about that. All right. So that means. Also, did he say anything about stability? Didn't say anything about stability. Okay. I'm just going to write out the zeros and the poles. Just make it easy. So our zero in this case is negative 25.641 times 10 to the third. And it's radians per second. Would that be on the left half of the real and imaginary axis, or a left half of the imaginary axis, or the right half of the imaginary axis? Left? I agree. Okay. And I'll do the poles. So we have negative 9.461 times 10 to the sixth, comma 5.004 times 10 to the third, plus or minus J 580.538 times 10 to the third. These are all radians per second. Are those in the right or left half plane? Technically, there's 3 of them. Is this one in the right or the left? Left. Is this one in the right or the left? There's 2. Are they both in left or right? I agree. So technically, those are unstable. Technically, that is stable. Technically, that is stable. But since your poles are in the right half plane, your entire function is unstable. Technically, in this one, no. So, all right. So, op amps suck. Any questions? No? All right. Cool. So, like I said, this will be on YouTube. I will try to talk to HCAN people to get that up as soon as possible. I have 2 more if you want to watch those from the previous semesters. Like I said, one from a year ago has op amps. One from last semester does not. But both of them have the other 4 topics. So if y'all wanted more study material, those exist. So, yep. All right, cool. Peace. Yep. I didn't expect it to take the entire time, but it did. Well, I was a little late as well, so that's on me. Yep. Oh, it didn't stop recording. It just stopped showing my screen. So it was recording the entire time. Someone asked about if there's going to be 2 recordings. Yeah. No. Yeah.